All right, good morning. How's everyone feeling? Are you okay? Yeah? Well, let's try it again. How are you feeling? Yeah? Okay, great. Yeah, it was a great party last night, it sounds like. All right, so we are here. We're back. Day number 2 of App Builders 2019. We're going to kick it off with not only one, but 2 speakers who's going to give a really interesting talk, I think. And they're going to talk about sharing code between iOS and Android. The holy grail, right? Like, how can we write code once and run it on both platforms? These guys are both developers at Ubiq, which is a development studio here in Switzerland. And they've been sharing code a lot in their projects. So they're going to tell the stories of that and how sharing native code compares to other frameworks like React Native and Flutter and things like that. So, since this is the first speakers of the second day, please give an extra, very, very warm welcome to Nicolas, Märki, and Joseph El Mallah.
All right, thank you. Good morning. Thanks for the introduction. I think you already said a lot about us. This is Joseph. I'm Nicolas. We're both iOS developers at Ubiq. So just a few words about us. Ubiq was founded about 9 years ago, and we're in the center of Zurich, and about 30 people right now. And we do mobile apps. And there we really focus on native, as a lot of you do, I think. And we think it's just the best way to get the most out of the platforms that we have. Just some of our projects that you might know are Meteor Swiss, Won't.Afo. Fun fact, it almost was called Democrap. But then we went for Won't.Afo, or SBB. And right now we have about 30 apps, or 20 in the App Store. And what a lot of those share is code sharing. So even though we do native, we think that there's a lot of business logic and code that actually doesn't make sense to write twice, and you don't end up with a better user experience just writing it twice. So to get started, we'd like to look at a few examples where we exactly share code.
So let's take the first example, our app in Meteor Swiss. As you can see, the first screen here, the reordering of the home screen is made, the code is made for the UI in native code, but the logic to know which style goes where and how do we reorder them is written in shared code and then shared between both platforms. So we write it once and then we deploy it in both. Then the second example is our map engine. We have written a map from scratch. So the shared code will read the data, parse it, and then also issue the OpenGL codes for it. So we have the same map twice on Android, iOS for the same code. Third one is how we can issue drawing calls directly on the native. As you can see, the temperature graph and also the precipitation, they are also written once and deployed on both platforms. Another example is the Viadi SBB app. And here we can see for the search. And for the search one, you can see that it's reading from a database and also is computing the distance between what the user is writing and what we're showing on the screen. And also after the user does that, we save it in the history. And all of that is done with the shared code. Same thing here for the reordering and also for proposing tiles that can be interested for the user. So we're going to present 3 ways to do that. And we start with the first one, the C++.
C++, perfect to start a day, right? So especially for the maps where we use a lot of OpenGL, but also other business logic, we write a lot of C++ code. Just to give you a little bit of background about C++ on mobile. On the iOS side, it's fairly simple. What you do is just rename a file from .m to .nm, and you're ready to write C++ code. And you actually get some nice new features like this auto keyword that you can use if you still write Objective-C code these days. And so yeah, yesterday was an interesting talk about how you can actually embed this in Swift. You'll need to do some wrapping, but it's still fairly easy. On the other side, on Android, first part also quite simple. What you do there is create or define a native method. And what's happening is that they have this concept of JNI, which stands for Java Native Interface, which is a bridge between the Java runtime and the native code that's running underneath. So if you expose a method with this native keyword, you basically tell Java that you will later on provide this with a native implementation, and then you're ready to use it in Java. Now what you have to do to expose this is something like this JNI export JString, JNI call Java, com example, hello. It's complicated and you have to keep to this formatting, otherwise it won't work. When we started writing C++ code to share, we actually wrote a lot of this JNI bridging stuff, and it's kind of annoying. And then luckily we discovered a Djinni, or actually Djinni like that. Djinni is a code generator. So basically what it does is that it builds on one side Objective-C++ wrapper that you then can use with Swift, and also does some bridging and wrapping there. And on Android, it creates all those JNI bindings for you. To do that, they provide an interface language where you can specify exactly which feature should be available. And the project was released by Dropbox in 2014. So let's have a quick look at such an example, just to give you a bit of a feeling. With this interface definition language, you have concept of records on top, which basically are models that you can share, and interfaces, which you would then either implement in C++ or Java and Objective-C or whatever you feel like doing. Just to give you a little bit of feeling how this would affect you if you feel like you want to start with this, what you need to do first is to check out the master branch from this project and then write these interface definitions. And then you call this Djinni run, which is a build tool that you just pass this interface file, and then it will provide all the bridging files for both platforms. And then, we add these files to each project and you're done. So comparing to writing all this bridging yourself, this is a lot easier. So just a few words for our setup. We actually forked Djinni, and the reasons for that are that we also added a parser back in the days where Codable wasn't available. So we generate all the parsing stuff inside of the generated models. And then we also added a few annotations like nullability and a few keyword checks, because our Android developers kept on writing ID into the models, and then we had some problems on iOS. And last but not least, we also used to do Windows apps, so we also extended the generator to build the bridging there. Few more words about the setup on iOS. What we do there is we have a submodule where we share the C++ code, and then add this Djinni run command to the run script phase. We use a make file to trigger the call for each Djinni file, and then we add all the files to the app project. We started out with building the C++ part first as static library, but we moved to adding it directly to project because C++ is a little bit tricky sometimes. And you just want to get as much ID support as possible. And with this setup, you actually end up being able to set breakpoints and everything inside the C++ code. On the Android side, the setup is fairly similar. On Android, we also use a submodule for the C++ code, and there right now we manually trigger the make file to build the Djinni models. And on Android, we rely a lot on the Android Studio SDK tools. So we use CMake plugin to read all the generated files. We use the NDK, it's a native development kit, and also install the LLDB debugger. And with that setup, you're also able to set breakpoints and everything inside the C++ code in Android Studio. So now, just to give you a little bit of feeling of the workflow to add a new feature, we want to present like the 7 thinking steps of adding a new feature to code. We're also going to share a few Medium articles, published them this morning. So this is really just to give you a bit of a feeling how complicated this is. So the example that we chose to present is the Levenshtein distance, so the editing operations between 2 strings. So like from AABC to AADE, we need to change 2 characters, so the distance is 2. So what we need to do to add this to the project is create a new Djinni interface definition file, and then write the interface definition, which is fairly simple. On iOS, then we build the project once just to generate the new files, and we manually add them to the project. Step 5 is that we create the C++ implementation file and write C++, because we all love that, right? And right away you're ready to use it in Swift or Objective-C. Now step 8 of 7 is to run this make call for Android to build the Android Djinni wrappers, and then also with the make file it will automatically discover the C++ code, and you will be able to call those in Java or Kotlin. So a few advantages of C++ from our side is that it's a first-class citizen on both platforms, so they both rely on C++ as well, so integration and support is quite well on both platforms. The language itself is super fast and mature, something that we benefit a lot, especially for graphics and OpenGL stuff, but also everything that you need to do a lot of computations. It's good to have an efficient language. And with this Djinni setup, actually the whole bridging is not that complicated. You still have to do a few steps, but it could be way worse, or it was way worse. Now, a few disadvantages is, number one, it's C++. The language has a certain beauty, but it's still so easy to mess up, and if you have someone who doesn't really know it well, we just lose a lot of time debugging there. You also need another language to define the interfaces. It's a fairly simple one, but still, if you start with Swift, and then you need to transition to this IDEA language, and then to C++, just always a bit of a mind shift. And finally, the support in the IDE or debuggers is quite good, but still not as good as with the primary language. Especially on Android Studio, you actually will end up with 2 separate debuggers, one for the Java Kotlin part and one for the native C++ part. And also, maybe worth noticing is that Djinni has a little bit of overhead, so if you do a lot of calls up or down, you will also always lose a little bit, so you might want to try to encapsulate calls that you don't do too many small calls. And last but not least, unfortunately, Dropbox announced that they stopped maintaining Djinni just a few days ago. We think it's not such a big deal because C++ as well as Djinni are very mature, and we don't expect that many changes, but still, we were hoping that they would continue improving it even further. Okay. And C++ now. Let's look at another language.
So now let's see how we can share code written in Java between both platforms. So to do that, we use something called J2 Objective-C, which is a Google open source project, and it is, by definition, a source-to-source compiler. So it takes the Java source. For that, you need to own the Java source. You have access to the Java source code, and then it's gonna be you're gonna be running this Android Java, the Java on the Android platform as usual. But when you use the J2 Objective-C, it's gonna generate Objective-C code for you from that source Java code, and then you can run native Objective-C code on your iOS. So here's a sneak peek what you can do actually with it. You can set breakpoints, debug, step through with Java code inside Xcode, and you can also have a look at the variables and also at the console at the same time while your app is running, of course. And on the right, you can see that we created a small demo for this talk where we take the game of life. It's an open source project on GitHub written in Java. So we took this core out of the GitHub project, put it inside our iOS app, then run J2 Objective-C, and now we can write the interface in Swift, and then call this core function straight away from Java, of course, after being translated to Objective-C. Now, first let's start with the limitation, before we get too excited. It does not do UI, so we still need to write our own UI, so it's not a cross-platform language, it's just to translate the Java backend or business logic. Then also it forces you to have bridging headers inside your Swift project. If you have already Objective-C, then this is not an issue, but if you have a pure Swift project, then you have to introduce bridging headers. It also have a limited set of what is already capable of being translated from the GRE, so you don't have access to the full GRE. We have a limited set. Of course, it's more than enough, but still you cannot use every single call in the GRE. Then also third-party libraries. We have to make sure that a third-party library that we use in the Java code can be transpiled or can be translated using this J to Objective-C. So it's good to just do some research or try it out before committing to a third-party library inside your code. Now the requirement, let's say you decide to do that. So you need the usual iOS setup, Mac plus Xcode. You need a GDK of 1.8. And here we have a funny story. It should be 1.8 because on the official documentation, they say it supports starting 1.6, I think, but we could not make it run except on 1.8. So we lost like 1 day just trying to install GDKs. So this is important. Then the third one, we need to grab the translated GRE. So Google publish regularly some releases for this translated GRE into Objective-C. So we don't need to compile it locally, but you can also compile it locally if you want. In our case, we took it directly. It's 1.7 gigabytes, so you can go grab a coffee while it downloads. Then we start. We open our Xcode project. First thing, we need to define the path to tell Xcode where this downloaded file is. We just created a custom-defined variable, and then we put the path. Then we can use that to specify the framework library and user header according to it. And then you can see that it should end with framework, lib, and include. That's what it comes to specifying path. Now Xcode knows about all the path where it needs to find all these files. Then second thing, we need to tell it to link this library, and then we just need to add these 3 libraries into it, and then the ugly part is finished. Now we need to tell Xcode every time you encounter a Java source file, do something, run J to Objective-C. And this is made via the build rules. So first we need to make sure that our target is selected. Then we go to the build rule tab, add plus, and then we can specify that it's a Java source file. So basically we're telling Xcode every time you encounter a Java source file, run this script. I will explain it more here. So the most important part of this script is this line where we tell Xcode to run the command line tool, J to Objective-C, with a bunch of other flags. What is important for us is that we specify a source path where our root Java folder is there. Then we have to tell Xcode that once this command is generated, there will be 2 output files that you need to care about. It's one that ends with .h, one that ends with .m. Actually, it's the same Java source file that was translated into Objective-C, so the header and the implementation. Then J to Objective-C run without ARC. You can specify ARC, but it is recommended to run it without auto-reference counting. So in our case, we run it without auto-reference counting. We let it do the reference counting itself, and we have to flag to the compiler just to overlook it when it comes to ARC. That's it. Now we can go ahead and use the Java code inside our project. So if we're coding with Objective-C, we need just to import the GRE emulation, and then every other class like we do normally. In Swift, it's a little bit more complicated because we need to have the bridging header, and if you have it, good for you. If not, create it. And then we have to import the GRE emulation and every single class that we intend to use inside Swift. There's one tricky part that we were not able to solve in a nice way. So every time you run the project from a clean state, so the first time you download the project or the first time after you clean it, you're gonna have this error showing because the bridging header are gonna try to be pre-compiled, but since we did not run the J to Objective-C build rule, so we don't have actually these headers. So Xcode cannot find them. We did not find at least a way to switch the orders, but what we do is just we comment out all that file, run it once, comment back in, run a second time. And this we need to do every time we clean or when we first install the project. But later, for every single other build, it works fine. If you have any solution for that, let us know also. Now calling the Java code, like a small example, how would it be? How would it feel like in your project? So here I initialize the board, and this is the class translated from Java. It looks like that. I initialize it, I pass in the board size and the probability for the cell to be alive. Then inside my game logic, which is a timer for every 1 second, I call update, which is also a function that we got from the Java core file, and the display board, which is a function of a protocol that we conform to. This protocol is also coming from Java. So far, we did not have to write a single line of logic. Then also, this is the function where we loop through the grid. So we take every row, and then for every row, we're going to take the cells inside that row and cast them. As you can see, there's a lot of casting. I will mention what happens later. And then here, in this case, I just printed, but in the demo project that you can get from GitHub, we have actually the code that updates the UI. So this is a small idea of what you would expect to have if you run a Java code inside the Xcode. In Swift, it's going to be a lot of unwrapping, and unless you want to put a lot of guards, then this is the solution. Yeah, it can break, but it keeps the code a little bit fairly simple to read. So keep in mind, reference cycle, this is important. So the Java garbage collector take care of reference cycles. But when we translate them into Objective-C, the code will leak if we don't take care of it. So it is recommended that we annotate our Java code with the annotation @weak. Then the J2 Objective-C tool will recognize this annotation and generate a weak reference when it translates to Objective-C. Also, there is a handy tool written by the guys from J2 Objective-C. It's called the Cycle Finder. You can find it also in the same folder that you downloaded. You just run it on your Java code base, and then it's going to print out all the loops that it detects. And you can then assess if it needs a week or not yourself. Multi-threading is very important for us, at least to keep a fast app and not blocking one. So J2 Objective-C supports thread class, so you can write multi-threaded code. It also maps the synchronized from Java directly to asynchronized from Objective-C. And then it also supports it has a full support for the atomic package. So, last. It's Java code base, so there's a lot of code already there available. There are also a lot of Java developers, and also there's a high chance that somebody knows Java already in your team. And also we have nice Java IDE, and we tried to write Java in Xcode, not a good idea. Then also the server code can be reused sometimes for some logic, since our servers were written in Java. Also we can debug using the Xcode project, and it's also fairly an easy setup compared to other sharing techniques. Now, the disadvantages, it's transpiled, so you have to keep in mind that it's transpiled. So there's no guarantee that the semantics, so whatever you wrote in Java will be executing. It will translate successfully, but it might not execute the same thing as it is executing in Java. So it's really important to write unit tests. And J2 Objective-C supports JUnit translation, so you can write your unit test in Java also, and then have the tool translating them to Objective-C, and then running the test natively on the Xcode project. Then you are sure that it's going to work. There's a lot of casting and force unwrap in Swift. It's slow a bit, the build time, because we need this extra step to transpile the Java code. And also it makes the app size a little bit bigger. Then also we can use some of the GRE, just the translated one already, but there are a lot of them. And also we are limited with the third-party library. Now we go through to the last way, Kotlin.
All right, let's talk about another language, Kotlin, or Kotlin native to be precise. So I guess all of you know Kotlin, or at least the Android developers, I hope they do. It's an open source language by JetBrains. It's now getting more and more used in Android. It's fairly new, 2011. And what's nice about Kotlin that there's a project or part of it, it's called Kotlin Native. And that is basically LLVM backend. So what they do is generate this intermediate code that then LLVM can use to build or to compile it to native Android, iOS, macOS, or pretty much everything. And someone yesterday, I decided that this is perfect to do a live demo. So it was a long night. I'm an iOS developer. Please be nice.
It's because they released the new plugin.
Yeah, there's actually a new plugin that I would like to show. It was released a few days ago. I installed it yesterday, so let's hope that it works. So what we have here is pretty much an empty project, just as a view controller. And then what's interesting is in the build phase, we have this Gradle or Gradle call that triggers this Kotlin build to generate a framework from all the Kotlin files. We don't have that published yet, but if you're interested, hit us up and we'll also share this little sample. So basically every time we build, it will look through all Kotlin files and build this native framework here. So the example that I would like to show again is the Levenstein distance between two strings. So what I'm going to do now is just add a new file. Let's call it Levenstein.kt. And now I'm actually head over to this nice site of Rosetta Code, if you know it, which has like Levenstein distance implementation for, I think, 90 languages. So here I just look for the Kotlin one. And then I'll simply copy this implementation. One thing that I realized yesterday is that Kotlin also changed the language a bit. But if you are Swift developers, we're kind of used to that, so it should work. And now I'll just build this once. Which may take a while. That's how it works. So yesterday was an interesting talk about the similarities of Swift and Kotlin, and that's why we think that this will be really an interesting solution, because then you can a lot easier transition between the two worlds. So now that I built this, you see that this Levenstein.kt already appears in my project, and I can call this distance. How did I call it? Levenstein. All right. Levenstein between, say, app builders and some people. And then I'll just print this. And let's see if this works. Okay, so you see we compute something, but I think the distance would be a lot smaller because we are all awesome, right? So what should be possible, or at least what I did manage to do yesterday, is actually set breakpoints and get code highlight inside of Xcode. So as you know, Apple kind of improved the whole plugin setup a while ago, or pretty much broke it. But what you still can do is install new languages. So there is a plugin that you can install inside Xcode that will enable a few features to work with Kotlin directly inside Xcode. If that isn't enough for you, you can also install AppCode, the IDE by JetBrains, who built Kotlin, and there you have a bit more advanced plugin to develop Kotlin as well. So as I said, Kotlin is a fairly new language. It has a lot of features that make it easy to use. It's fairly similar to Swift, and you have some IDE support in both Xcode or AppCode. Now, what's important on the other side, that this Kotlin native project is still in a beta, and it's very beta-ish state. So there are things like threading and dependencies that don't really work out. So this is really just very early stage, and we have never used it in a bigger project and don't really recommend to do so now. But we still think if this goes further, that this might be a really interesting approach. But it's worth noting to note that the setup that we have now is not official. There are some plugins for both IDEs, but you don't really find any tutorials or a big community who already works with that. So when you're stuck somewhere, you're probably just stuck. But we do hope that at some point we can write more Kotlin or easier code than C++. But nevertheless, even with C++, I think we share a lot of code now, and it makes life a lot easier. So
let's finish up with the conclusion. It's been a lot of notions. So in general, code sharing, why do we do it? Why do we bother do it? Because first, we can still write native UI, and we think this is the best way to deliver the user experience to the users, actually. Then we have one business logic, so we write it once, and theoretically, we can be faster in implementation, but sometimes we get stuck. And also, we have less maintenance later. Once the code is written once, then we need just to maintain it once, and not on 2 platforms or 3 like we had with the Windows. And then we can benefit from bug fixes. So every time we find a bug on a platform and we fix it, it's actually propagating to the other platform automatically. It's also a nice feature, side effect of it, that it forces reusability and modularity from the team, since we need to think what needs to go in the shared part and what can go in the presentation part, which is natively written. Now, disadvantages. Oops. So we have the learning curve. This takes a while to learn, especially if you join newly the team. You have to put in the time and effort just to learn the whole ecosystem. Then also, sometimes the setup takes time, especially if it breaks for a newer update or a different Xcode version. Then we put in a lot of effort sometimes to have it fixed, of course, overnight or by 2 days, just so we can continue with the development. And also, it forces a sort of a code style and a code language from us, since we have only these 3 options available and Kotlin not really ready. So we are forced to write either in C++, either in Java, but we cannot choose the 3rd language as our own. And plus, in each one, in the Java, also we have limitation, and in C++ also we have some limitations. So this is to keep in mind. So the moral of the story, yes, there are disadvantages, but it's worth taking the time to solve them and to benefit from all this code sharing. So that's all we have to say for this presentation. Please feel free to talk to us, to ping us, to write to us if you have any question. Also, we have published 2 articles detailing how exactly you can set up the Java. Here it was a short talk, but in the article it's detailed step by step with a lot of more remarks and tips. Also the same for the C++ sharing. And in case you are interested in joining us at Ubik, feel free to hit that URL at the bottom. Thank you.